All right, welcome guys. We're going to start chapter 4 in this lesson. And chapter 4 is all about solving and applying proportions. Solving and applying proportions. So to kick it off here in 4.1, we're just going to have you solve a simple problem on your own. I am buying orange juice and I want to know what the best deal is on orange juice. I'm in the grocery store and I see that there are 3 different orange juice options, 3 different sizes and 3 different prices. And I want to figure out what is the best deal for me. So pause the video, figure out the best deal for me, and we will go from there. Okay? Hopefully you've tried it, you've unpaused it, and you're going, what is the best deal? Well, just kind of thinking it through, your gut reaction might have been, well, this is the cheapest. But I didn't ask for the cheapest, and I didn't ask for the largest. I simply asked for the best deal. What does the best deal mean? Well, the best deal would imply that I'm getting the most bang for my buck, so to speak. I'm paying the least amount per unit I am getting. So how could we have solved this? Well, we have our prices here, but the volume is also changing. What I want to do here is I want to break it down so that the volume's all the same, and I can figure out what I'm paying for per volume. You can do this by dividing the price by the volume. The price by the volume. Okay? If I do this, I'm going to figure out how much each ounce of juice costs. If our volume is in ounces, and I divide the price by the volume, I figure out the cost per ounce. You might have seen your parents do this at the grocery store, or even if you go to some grocery stores, in the corner of the price tag, they'll actually tell you the price per ounce. How do they get that? They divide the price by the size. Okay, so if I do this, I got my calculator here. 0.72 divided by 16 gives me 0.45. Okay, and again, what does that do for me? That is the price per ounce. That is, I'm paying roughly 4.5 cents per ounce of orange juice. Okay, well, what about 1.2 divided by 32? Well, when I do that, I get 0.0375. So 3 3/4 cents per ounce. A little cheaper. And then finally, 1.6 divided by 64, and I get 0.025, which is 2.5 cents per ounce. So what is the best deal technically, the most bang for my buck? The 1.6 would be. And this is what we're going to get into. This is an intro problem into chapter 4. Chapter 4 is, again, all going to be about ratios and proportions. And we're going to dive into solving problems like these. Okay? So again, we're going to be all about ratios and proportions. So what is a ratio? Well, a ratio is a comparison. Again, please write down anything I do on the smartboard on your notes. So if you need to pause it and go grab a notebook, please do so. A ratio is a comparison of 2 numbers by division. A comparison of 2 numbers by division. It's what we did above in the orange juice problem. I divided the price by the volume to get the cost per ounce. Okay, so let's look at a couple more examples. And what's interesting about this is it's actually very applicable to science. Okay, a lot of times in science, we start in certain units and we want to transition to other units, and you do it by multiplying ratios. So let's think through an example. How many minutes are left in your shift if you have 2.5 hours to go? If any of you have jobs or have started working yet, I'm sure this might be something you do. How many minutes are left in your shift if you have 2.5 hours to go? Well, you might be sitting there going, okay, Mr. Carter, I can figure that out. That's pretty easy. I've got 60 minutes in an hour. Well, I've got 2 hours, so now 120 plus a half hour. I've got 150, okay, 150 minutes, okay? What your brain is doing there, whether you realize it or not, is multiplying with ratios, okay? You're multiplying with ratios. You see, you start with 2.5 hours, okay? We start with 2.5 hours, but I want to convert that to minutes. How can I do it algebraically? Well, I can do that by multiplying by a common ratio. What is a common ratio? It's a ratio we know, and it helps us transition our units. So I have 2.5 hours, okay? I want to get that into minutes. Well, let me back up here and talk about a similar concept. If I have 3/5 as a fraction, and I multiply it by 2/3, I'm going to end up with 2/5. How can I tell you that? Because when you multiply fractions and you have the same thing in the numerator and the denominator, it cancels. If I had 5/2 times 7/5, I know it's going to turn out to be 7/2. Because again, if you multiply fractions across and you have the same thing in the numerator and the denominator, they will cancel. Okay, so what does this apply to us here? Well, you see, I'm going to almost do that, but I'm going to do it with units. So I have 2.5 hours here, and I want to get into minutes. So I don't want to have hours anymore. So I'm going to go ahead and put hours in the denominator. Why? Because if I multiply by a common ratio and hours is in the denominator, they will cancel out, which is my goal. But what do I put in here numerically? Okay, well, on the bottom, I want to get rid of hours, but the question is, what am I replacing hours with? Well, I'm replacing hours with minutes. So we're going to put on the bottom of the ratio the unit we're trying to get rid of, and we're going to put on the top the unit we want. I want to get rid of hours, so I put it on the bottom. I want minutes, I put it on the top. Now the question is, I know my units here. I have hours, and I'm trying to get it to minutes, but what do I do here? Well, what is a ratio between hour and minutes? This is why it's called a common ratio. You all can probably tell me through your computer screens that there is 1 hour in 60 minutes. So what do I do here? Well, now I'm just going to execute the multiplication. My units have canceled, so now I'm in minutes. And if I just do the problem, 2.5 times 60 divided by 1, I get my answer. Well, we know dividing anything by 1 is just itself, so that doesn't really matter. But what's 2.5 times 60? 150 minutes. The very thing that if we just thought it through earlier, we would have ended up with. So why are we doing this? Because we can't always just think it through right away. A cheetah runs 300 feet in 2.92 seconds. What is that in miles per hour? That I can't think of right off the top of my head. But if I do multiplication with ratios, I can figure out the units I want. Again, this is going to be huge in science. So let's talk this through. A cheetah is running 300 feet in 2.92 seconds. If you think you could figure this out, go ahead and give it a shot. Otherwise, stick with me. So a cheetah is running 300 feet in 2.92 seconds. Now, unlike the last problem where we only had something on the top, here we have already are starting with a ratio. But we're not going to handle it really much different. We're just going to try and get the units we desire. Now, we're going to need a couple more steps because I need to transition feet into miles, and I need to transition seconds into hours. So we're going to have a couple more steps, but it's the same process. So let's use ratios to get down into the units we want. 300 feet in 2.92 seconds. Well, I need feet to end up being in miles. So my first thing is I want to get feet into miles. Well, as we learned in the last problem, I want to get rid of feet. So I know that unit's going to go on the bottom. What am I replacing feet with? Well, feet is being replaced with miles. How many feet are in a mile? Well, that is a common ratio. Some of you might know it, maybe some runners in the group. But if you don't, there are 5,280 feet in 1 mile. So I'm going to multiply this ratio of 300 over 2.92 by the ratio 1 over 5,280 to get from feet into miles. Are we done? Well, no, look at the units we have. Right now, we have miles per second. But is that the goal we want? No, we want to get miles per hour. Well, let's multiply by another ratio. So I've got the miles I want. Now I need to focus on seconds. Do I want seconds? No, I want to replace seconds with hours. Well, you're probably telling me, okay, so seconds goes on the top. Now, pause. Why would I want seconds on the top? Well, we said earlier that they need to be in opposite parts of the fraction. Feet's in the top, therefore it needs to go on the bottom to cancel. Since seconds is in the denominator of my first fraction, it needs to be in the top of this fraction. So seconds goes on the top, and I want to replace it with hours. Now, unlike the others, I know how many minutes are an hour. I know how many feet are in a mile. Maybe I don't know how many seconds are in an hour. Well, you can use a common ratio kind of as an in-between. Because most of you don't know how many seconds are in an hour, but I know you know how many seconds are in a minute. Will this make another step for us? Yes, but can we still solve it? Sure. So I'm going to cancel out seconds and go into minutes. How many seconds are in a minute? There are 60 seconds in 1 minute. Now, do I have the units I want? Well, I'm closer. I'm now to miles per minute. But I want miles per hour. Well, how do I get from minutes to hours? Minutes will go on top because we want to get rid of that, and we want to replace it with hours. Now, if you look at all the units we've crossed off, what are we left with? Miles per hour. How many minutes are in an hour? 60. So all of you, what I hope the pattern you're seeing is we're going to cancel all our units out. And as we cancel our units, we just put appropriate ratios in between. I want to go from feet to miles. So there's 5,280 feet in 1 mile. In doing this, there shouldn't be any guesswork about what the multiplication ends up to be. If you follow your units through, canceling them with common ratios, you're just left with a multiplication problem at the end. Now that my units are correct, I know I need to do 300 times 1 times 60 times 60 over 2.92 times 5,280 times 1 times 1. Now, you know the ones don't need to be in there. I just put them for the sake of hopefully helping the problem make sense. But when I multiply the top all together, 300 times 60 times 60, I get 108 and 4 zeros. So 1,080,000 divided by, when I do 2.92 times 5,280, I get 15,417.6. If I divide those two numbers, I get 70 0.05, and that's rounded. So if I know a cheetah can run 300 feet in 2.92 seconds, then I can use ratio multiplication to figure out that that's equivalent to 70 miles per hour. Okay, if you are confused on this is a great chance to pause the video and email me. You will be doing a couple more examples in your homework, but let me know how I can help clarify that. Otherwise, let's move on. So let's go back to fruit. We talked about orange juice earlier. Let's keep with the theme. If I have 5 apples for every 6 bananas in my pantry, how many apples do I have if I have 12 bananas? What about 9? Okay. I want you to pause the video and think this through. Okay, so now you've paused it, you've thought it through, maybe you have an answer. If I have 5 apples for every 6 bananas, how many apples do I have if I have 12 bananas? Well, what do the amount of bananas increase by? Well, they increase by 6, but not only do they increase by 6, but what I hope you realize is they doubled. So theoretically, the number of apples should double as well. Okay? If the number of bananas and apple, or if the number of bananas double, then the number of apples should double. So 5 should go to 10. What about 9? Well, I increased by 3. It's a little more complicated. So kind of like I did with the ratios, we're going to show you an example here and how you actually solve this problem with something called a proportion. A proportion is when we set 2 ratios equal to each other. We set 2 ratios equal to each other. We will then cross multiply to solve. We set 2 ratios equal to each other and we cross multiply to solve. So what's this look like? Well, if I have 5 apples for every 6 bananas, and if you didn't get that definition quite written down, scroll back in the video a bit and pause it and get that written down before we continue with this. So if I have 5 apples for every 6 bananas in my pantry, I could write it as a fraction or as a ratio. 5 apples for every 6 bananas. We know the ratio is the same, so we're going to set up a proportion where we set another ratio equal. I have 5 apples for every 6 bananas. How many apples do I have if I have 12 bananas? Now remember earlier, we established the answer probably should be 10 just by using logic. Let's see if our definition for fraction or for proportions works. So right now, I don't know how many apples I need. So what I'm going to do is called cross-multiplying and dividing. When you have 2 proportions equal to each other, if I want to get the variable by itself, what I hope you see here, let me get rid of the labels so it's a little clearer. What I hope you see here is this is just a chapter 2 problem. How do we get x by itself? Well, it's being divided by 12, so we multiply by 12. In other words, you multiply across and then you divide. I'm going to multiply 5 by 12 and then I will divide by 6. Personally, I don't care how you think about it. If you think about multiplying 12 by both sides and then you do it, that's great. If you like the idea of cross multiplying and dividing, that's also great. So I need to multiply both sides by 12. Well, 12 times 5 is 60. And 60 divided by 6 is 10. So what's the theme here? Well, we multiply across and then divide, and that gave us how many apples? Now, why is that important? Because while you can probably logic through 5 apples for every 6 bananas means I should have 10 apples for 12 bananas because it's a nice easy double, 9 is a little bit trickier. Well, with this method, we can solve it just as easily. Again, I have 5 apples for every 6 bananas. What if I have 9 bananas? It's the same problem, except now I'm just going to multiply by 9. Please notice that when my bananas are on the bottom, my bananas stay on the bottom for the second side of the equation. My apples are on top, they're on top for the second side. Make sure you maintain that consistency. 9 times 5 gives me 45. And if we do 45 divided by 6 in the calculator, we get 7.5. So theoretically, if I have 5 apples for every 6 bananas, then I would have 7.5 apples for every 9 bananas. Maybe I cut one in half and add some apple slices. Okay? But the point is, while a nominal example, a proportion is when we set 2 ratios equal to each other. We will cross multiply to solve these. Let's look at a couple more examples. Let's say I have 18 over 50 equals m over 15. How am I going to solve this? Well, again, you could treat it like an algebra problem. Multiply both sides by 15 and solve. Or maybe you're seeing a pattern in this and you see that you could also just multiply across and then solve it. I don't care what you do. I'm going to do it the first way. I'll show you how to do both, whatever makes more sense to you. So if I want to get m by itself, I'm going to multiply both sides by 15. 15 times 18 gives me 270 divided by 50, and they cancel over here. 270 divided by 50 gives me 5.4 as my answer. Now you heard me use the phrase cross multiply earlier. What does that mean? Well, another way to solve the proportion is to simply multiply across the equal sign diagonally, and it sets up a little algebraic equation. 18 by 50 gives me 270. 50 times m gives me 50m. And you end up solving the exact same problem. My point is, I don't care how you think about it. I just want you to solve it using correct algebra. So whether you want to do the diagonal multiply, personally, I think thinking about it in blue is a little easier. Why? Because it's exactly what we did in chapter 2. But I will leave that up to you. Nonetheless, your answer should be 5.4. Well, what if we get a little more complicated? X plus 4 over 5 equals x minus 2 over 7. This is where cross multiplication can become pretty helpful. You see, I want to get the variables by itself, but before I do, I want to get rid of the fractions. So what I could do here is I could multiply across the equal sign diagonally and then solve from there. So I multiply x plus 4 times 7, and I multiply 5 by x minus 2. Once I do this, I'm going to go ahead and distribute, and I get 7x plus 28 equals 5x minus 10. From there, I'm going to subtract 2x from both sides, and I get 5x plus 28 equals negative 10. Subtract 28 from both sides. And I get 5x equals negative 38. Sorry about that. Divide both sides by 5. And I get x equals negative 7.6. X equals negative 7.6. Okay? That is cross multiplying and dividing. Again, as you saw earlier, it is no different of a process with proportions than if I would multiply the left side by 7, then multiply the right side by 7. Essentially, you're doing that just in maybe a little bit less steps. If this is confusing to you, go ahead and shoot me an email and let me know so I can help you out. But this is multiplying across, okay? We do this with proportions. All right, let's try a word problem and then we'll call it a day. In 2020, Mr. Carter completed the Tour de France. No, he didn't. But theoretically, he did. So once I completed the Tour de France, biking 3,454 kilometers in about 86.3 hours, if I travel at the same pace I did in the Tour, how long would it take me to run 100 or bike 185 kilometers? Okay? This is applying proportions to real-world problems. Okay? Well, what's the first ratio they give me? Well, I'm told that I'm biking 3,454 kilometers in 86.3 hours. And I want to know how long it'll take me to ride 185 kilometers. Notice again, kilometers is on the same side. It's on the top in both. Well, I don't know how long that is, so I'll take a variable there because that's what I'm trying to figure out is the number of hours. Again, that I can set up the proportion because of the phrase same pace. So where are we going to go from here? Well, you have two ways of solving this, right? I want to get x by itself. Okay, so how could I do this? I can cross multiply. So that will be 3,454 times x equals 185 times 86.3. Now again, this is a public service announcement. I'm kind of glossing over the theory of cross multiplying. I've shown you how to do it a couple times, but I haven't really gone in depth about how it's the same as doing normal algebra stuff. If you are confused about why cross multiplying works and how it gives you the correct answer, my brief explanation earlier didn't make sense, please email me or talk to me in class so I can help you. Okay, 185 times 86.3. And I will get 15,965.5. And to get x by itself, then I will divide both sides by 3,454. And once I do that, I get x equals 4.62. That is a rounded answer, hours. So it's going to take me a little over 4.5 hours to bike 185 kilometers if I do it in the same time I did when doing the Tour de France. So to summarize the lesson, what's the moral of the story? Well, we learned about these things called ratios. Again, ratio is a comparison of two items by division. The one is divided by the other. The price is divided by the amount of orange. Why ratios matter, okay? With ratios, we can use it with multiplying by other ratios to get to quantities we want. Remember, we looked at a cheetah's speed in feet per second and what that would be in miles per hour. Okay, we used multiplying ratios by other common ratios to figure out a ratio we wanted. Then we talked about proportions. Okay, proportions is when you set two ratios equal to each other. How do we solve proportions? Well, we try and get the variable just by itself like we did in chapter 2 and what we've been doing all year. But one way of doing that is by cross multiplication, multiplying across the diagonal of the ratio and then solving from there. So that's 4.1. You're good to start the practice and have a great day.